Kia ora Year 12 and Year 11. In this video I'm going to go over antidifferentiation, which is backwards differentiation. So far we have learned that if we have a function f of x, we'll put an example in, so let's make f of x equal to x squared plus 2x plus 1. So if that's my function, I can find its derivative or gradient function, which is f dash of x. So for this example it would be 2x plus 2. Now for this simple function, I can draw the function here because I know it's a parabola and it would equal x plus 1 squared. So in this example, from our graphing unit, we know that it's going to look like this. This gradient function tells me the slope or gradient at any point on the curve. Okay, and so what we're looking for is, suppose that we wanted to find the gradient at x equals 3. So what I'm looking for is the slope of the tangent to the curve when x is 3. And I can find that by substituting in the value 3 here. And it would give me 2 times 3 plus 2, and that equals 8. So I've done other videos on that, and we've got the hang of that pretty well now. Alright, so what we're going to do now is we're going to learn how we can start with a gradient function, f dash of x, and work backwards to see what function it might have come from. Right, so moving on to the next slide. Let's start with oops, moving around. Here's my gradient function. So f dash of x is equal to 2x. So that's my gradient. What curve or function could have given me that gradient? So we're going to do this one by looking at the graph first, and then we'll see that all we're doing is reversing the differentiation process we followed. So this says that my gradient looks like this. Right? Remember the class where we had the function and we drew the gradient function. So thinking about that, what's that telling me about my function? It would be much nicer if I could do that on top of it, but let's get the idea. So this is saying at the point x equals 0, the slope of my curve is equal to 0. So that means it's got a maximum or a minimum, it's got a flat point in here. And out here, the slope is positive, and it's getting steeper as we get further away from x equals 0. So something like that. On the other side, the function is decreasing because the gradient is negative down here. So that, and it's also telling me that as x goes this way, the slope is getting more and more negative. So what I've drawn there is our basic parabola. And you can see that because if we start with the parabola and we differentiate, we get back to 2x. Now you can think about what we've done here is when we differentiate, we're going to drop the power by 1. So when I anti-differentiate, I need to be increasing my power and tweaking this number here to make it work. But there's a little problem with that, which is that if I had another function, suppose I had the same parabola, but I moved it up by 4 units. So here it is here. This should be called maths with bad drawing, but there you go. I know that if I differentiated that function, I would also get 2x. So what this is saying is that when I'm starting with the gradient function and I want to work back up to the function, there's an infinite number of members of the family of parabolas that could have come from, because they are all going to give me a gradient function of 2x. So when I antidifferentiate, I need to include a constant term on the end. I'm going to do that on a new slide. So if I have the gradient function f dash of x is equal to 2x, my antiderivative is equal to x squared plus c. And this is any constant, because you can see that if I've got the parabola y equals x squared plus 6, or y equals x squared minus 17, it doesn't matter. The first derivative, or gradient function, is going to equal 2x in both those cases. Same thing for this one here. This part here will differentiate to give me 2x, but we know that the constant term differentiates to nothing. So the trick with antidifferentiation is remembering that until I get given more information, and we'll come to that tomorrow, I'm going to have to include this plus c term on it here. So now we're going to practice doing some different ones so that we can see the pattern. So let's start with f dash of x is equal to x squared plus 4x plus 6. So the antiderivative of that function is f of x. Here's some new notation. So these two things tell us to do antidifferentiation on this function here. So f of x is equal to the antiderivative of x squared plus 4x plus 6 dx. Right, so now we're going to go ahead and do the antidifferentiation. Now, what will differentiate to give me x squared? Well, it's going to have to be something with x cubed, because when I differentiate that, I'm going to get 3x squared. So what I'm doing here is I'm adding 1 to the power. But I don't want to have 3x squared, I just want to have 1x squared. So here, x squared antidifferentiates to 1/3 x cubed. Let's look at the next bit. Here I've got 4x with an invisible power of 1. So the antiderivative of that part is going to be something x squared. When I differentiate this, I want to end up with 4x. So it can't just be x squared, because that would give me 2x, and that's bad, just like 3x squared was bad. So I need to match it to 4x. It's going to be plus 2x squared. And the last one, the plus 6, that's easy. That antidifferentiates to plus 6x. When I differentiate that bit, it will go back to 6. And lastly, and really importantly, I need to add on the plus c. Okay, on the next slide, I'm going to give 3 more examples. Here's the first one. F dash of x equals 3x squared minus 6x plus 8. Here's number 2. F dash of x is equal to x squared plus 3x minus 4, and we'll just do 2 on here. That'll do. Right, so antidifferentiating, I write this. F of x is the antiderivative, or sometimes we'll say integral, but not very much in Year 12. So f of x is what I get when I reverse differentiate this thing here. So what's going to give me 3x squared when I differentiate? Well, it will be just plain old x cubed. The next one, what will differentiate back to give me x? Will come from an x squared. So I'm trying to match up minus 6x, so here I'm going to have minus 3x squared. Here, the plus 8 is coming from plus 8x, and that's plus c. Okay, so we've found our antiderivative. There it is there. Next one. I'm trying to find f of x from the gradient function. So it's the antiderivative of x squared plus 3x minus 4 dx. Okay, so what will differentiate back to give me a squared thing? It'll be a cube thing. But I don't want 3x squared, I want 1x squared. So that has to be 1/3 x cubed plus, this has to be something with an x squared, but I want to have a 3. So it's going to have to be 3 over 2x squared minus 4x plus c. So the best thing to do with these when you start out is, and even when you have been doing them for ages, is to check back that when you differentiate that, you get back to where you started. So checking this one, we'll get 3 1/3 times 3 x squared plus 3 over 2 times 2x minus 4 plus 0 from that. So that's good. That gives us the x squared, that gives us the 3x, that gives us the minus 4. So that's looking nice. Okay, so here's a general rule. If we've got f dash of x is b times x to the power of m, then f of x will be this. It'll be x to the power of m plus 1. We'll leave the constant sitting next to it and we'll divide through by m plus 1, and then we'll have a plus c. For example, if f dash of x is equal to x to the power of 5, then f of x is going to be 1/6 x to the power of 6 plus c. Right, there are lots of examples to practice in New Lake on page 39. The ones towards the end have got some fractions, so you'll need to be especially careful with them. I'll do another video about those later on. Thanks for watching.